Hello, everyone. We're continuing our discussion of aromatic compounds. Now that we have an idea of what it makes, or what it takes rather, for a molecule to be aromatic, let's talk about other instances. And I'm going to be very clear as to what they ultimately mean. All right. So, looking at these three carbon cyclic structure, right? We mentioned that for this thing to be aromatic, just from the Huckel diagram, you want to only populate the lowest level, which is just one level. So you only want to have two electrons, right? That means that n equals 0 in the 4n plus 2 sequence. And what that means is that for this ring to be aromatic, because it has three carbons, that means 3 pi electrons, you got to get rid of one of those electrons. So you're talking about the cyclopropenium cation specifically, right? So that would make it aromatic. You're only populating the lowest level. Now, there is two other situations you can encounter because the ring, if it's still conjugated throughout all the carbons that make up the ring, and if it's still planar, you still have the situation for it potentially being aromatic. But here's where things kind of change a little bit because you will still have the same diagram for the three-member ring. But if you start changing the situation, right? Like if you have just populations of the anti-bonding orbitals right here. Okay, so a couple things about it. First things first, you don't have electrons that are fully paired up, right? This is technically a paramagnetic system, so that's already pretty bad. You want to make sure that all your electrons in your diagram are paired up, and ideally they are populating only bonding orbitals. That's what aromaticity is all about. You get stability because you're populating bonding orbitals. But the moment you start populating anti-bonding orbitals, and worse yet, the moment where you have unpaired electrons, this is what we would depict as saying, okay, this system, not only is it not aromatic, but because of the paramagnetic nature of it, it actually is a very unhappy molecule. So not only is this not aromatic, this is like you really going out of your way to make the molecule more unstable than it could have been otherwise. So if you get into a situation like this, the molecule basically is going to do whatever it needs to do to break away from potentially being in this aromatic framework. That could mean that the molecule will lose its planarity. It could mean that the molecule will break the hybridization, so the orbitals are no longer overlapping with each other. But yeah, if you have a count that is 4n, not 4n plus 2, the molecule is anti-aromatic, and it's because you're going to end up undoubtedly with unpaired electrons. Okay, and then there's another one that sometimes gets a little bit misunderstood or confused with anti-aromaticity, non-aromaticity. This will happen if you have electron counts other than 4n plus 2 or 4n. So same idea, right? The ring still has to be planar. The ring still has to have conjugation throughout. And then these terms apply, right? If you have the 4n plus 2 count, it's aromatic. If you have the 4n count, it's anti-aromatic. If you have anything other than 4n plus 2 or 4n, it's non-aromatic, period. But the premise is that it's still conjugated throughout and it's still planar. All right, so with that idea in mind, I think we're in a good position right now to talk about rings bigger than benzene. And not only that, but to talk about rings that are fused to each other. Because there's a lot of examples of this sort that are also aromatic. And there is a way to tell whether or not the 4n plus 2 rule is being fulfilled. Because at first value, you might be like, oof, okay, what the heck's going on right here with this system? Oh, and by the way, aromatic rings, with fused rings in the structure are known as annulenes. So these are two examples of them. All right, so the way we're going to try to determine whether or not this is an aromatic system or anti-aromatic or potentially non-aromatic is to basically follow a set of rules. The rule is that we want to go through a loop. Basically, we want to go from one end of the molecule to the other, but here's the deal. You have to go through the loop that has the most amount of carbons where the conjugation is present, okay? And so when you look at a molecule like the one up here, yes, we do have the six-member ring associated with benzene, six-member ring right here, six-member ring right there. But the conjugation, if you look carefully, you should realize all the carbons right here are sp2 hybridized, sp2, 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 sp2. That means that everything here has p orbitals that are aligned with each other, parallel to each other. So you don't just want to stick to the one benzene ring right here, because that will not give you the greatest amount of carbons in a loop. Instead, you want to cover the entirety of the periphery, basically, like the perimeter of the molecule. Let's put it that way. Okay, if you cover that, that takes more than just six carbons. You basically cover all of them. You know, all of the carbons present in this molecule. If you and it doesn't matter where you start. You can start right here and then basically trace it over. The idea is that you do have to complete a loop. And once you make a loop, you don't continue making further loops. It's just one loop, but it has to be the greatest loop in terms of carbon content. All right, and then for this one, same idea. The greatest loop is not going to be the six-member ring. It's going to be the ring going all the way around the perimeter of the molecule. Okay, so that's the first thing. Now, the second thing about it is that you want to count how many pi bonds you are going through as you know, look at the entire loop that you have generated. And what this means is that you want to count basically a pi bond if it is literally in the loop itself, right? So if you look at the molecules here, I'm counting 1, 2, 3, 4, 5, because those are the double bonds that are literally in the highlighted loop. Down here, we have 1, 2, and 3. That's what's highlighted in the loop itself. And what I'm basically stating on this next part is that it's okay that some of these double bonds are not part of the highlighted loop, because you still have polyconjugation as a result of the p orbitals overlapping with each other. So that's totally fine. All right, so everything is still conjugated, right? So those guys are not counted because they're not on the loop, but they are still overlapping. So to kind of account for that, you say, okay, you have the 6, the 7, you have the 4 right there. What you basically want to tell yourself is, do you have an odd number of pi bonds as you count this whole set of contributions? Or do you have an even number? If you have an odd number of pi bonds, you're going to ensure aromaticity is attained. And that's simply because you're looking for a 4n plus 2 count. If you have an odd number, you have one orbital that's by itself, and that's already the plus 2 count. But if you have the even number of pi bonds, that's when you're going to end up ultimately dealing with a 4n count for everything involved here. So, counting all these pi electrons, right? So I told you, count the ones in the periphery, but then acknowledging the fact that the pi bonds that are still present in that loop as a result of the polyconjugation. We're counting those two as well. We have 7 in total in this one. That's an odd number, so that will say that this whole thing is aromatic. Now, down here, on the other hand, because the carbons that make up the double bond that goes, up and down, are carbons that are falling within the loop itself, we're counting a total of 4 bonds, 4 pi bonds in this molecule. And because that's an even number of pi bonds, that's an anti-aromatic molecule altogether. All right, so let me show you 2 more examples for this to make sense, because the first time you see it, it's a little, it's a little bit not confusing per se, but it takes a little bit of time to acclimate to it. So we're going to do the same thing here. The greatest loop is going to be the perimeter of the molecules. That will be true for both of them. But one thing you should notice is that if you do go through the entire perimeter of the molecule, this one right here happens to have an sp3 hybridized carbon. So it turns out to be the case that if you do go through the entire perimeter of the molecule, that will be a huge mistake, because this carbon is not conjugated with the rest of them. So in reality, the biggest ring that you could go through as a loop that is actually conjugated is the 6-member ring, the benzene ring. Okay, and what that means is that the alkene, and I really mean it, the alkene that's here on the outside portion of the ring is not part of the aromaticity of this molecule. It's just a regular alkene. All right, and then obviously that only counts 3 pi bonds within that loop, so that makes it odd. That's aromatic. Okay, now this one, every single carbon in the sequence is sp2 hybridized, so you can go through that entire perimeter. And if you count the number of pi bonds, we got a total of 4, which will tell us that this is anti-aromatic. Okay, so one more example of this sort, a little bit more complicated. If you look carefully, if you scan through the molecule, you should see that there is no carbon without sp2 hybridization. Every single carbon present in the molecule has a double bond arising from it. So the greatest loop will literally be the perimeter of this entire molecule, right? So go through that perimeter, and then we basically count all the pi bonds that we see. And then notice that in this example, because of the greatest loop going from the outside of the molecule entirely, the carbons that are literally in the middle are not being actually highlighted in the loop. So even though we do have those double bonds there in the middle, we're not going to count them at all, because the one requirement is that if you do count these double bonds that are kind of not exactly going in the highlighted region, you got to touch the carbons with the loop at the very least. But these carbons in the middle are never touched by the loop, so we're not going to count those double bonds. So in total, we're talking about 6 pi bonds that make up the loop. And at first, you're going to say, all right, well, that it's an even number, so that's an anti-aromatic system. However, and this is a big thing that you have to watch out for, you got to remember that benzene and other aromatic compounds, they do have resonance structures. So you could literally draw a resonance structure for this molecule by simply moving this pi bond here on the top towards the left, or you could even do it the way I did right here. Is I took the pi bond here on the right side and I moved that over to the top portion of this ring, and then that started a cascade of pi bond relocations that gets you to this situation. And at the end of the story, you still have the same thing. You have the one 6-member ring that has the 3 double bonds within it, just like we saw right here. And then you have 2 that have 2 double bonds. So there it is, 2 double bonds, and then 1 ring that has 1 double bond. So it's still the same picture, but everything kind of has been reallocated. And if you go through the perimeter of this thing, now you realize, ooh, the count changes. The count is now 7 double bonds, basically an odd number. And between the even or odd number, if you do hit an odd number by doing a resonance structure for the molecule, then the molecule will favor the odd number, and so this will end up being aromatic. So just watch out for that, because that's an easy way to kind of fall under a false sense of anti-aromaticity. The resonance structures is to be consulted with. Okay, so that will end the discussion of polycyclic compounds, the annulenes, and in the next video we'll talk about heteroatoms and aromaticity. So I'll catch you on that one.